Let me actually upload the, yeah, so campus wire is down. Okay. Let me see. So here's I'm going to paste a link to the slides on Google Drive, so you should be able to download it directly from the link. So let's say another 2 or 3 minutes before we start, as the more students are joining now. Because campus wire is again down, I guess everyone is moving to these remote classes, and then the servers are just not holding up. If you have any questions, put it on the Zoom group chat here. As before, I won't be able to answer all the questions on the fly. However, I'll try to do so after the lecture is done, or you can wait for the campus wire to come back online, and then we'll be able to, you can ask the questions on campus wire, and then all of us, including the course assistant, we will be able to answer the questions as much as we can. Let's see. So let's wait another 2 minutes before we start. One more minute before we begin our lecture today. All right, shall we start today's lecture? So today we are going to learn a bit about the advanced topics. And then before the advanced topic, we need to talk about something called inference, or more like the generation. And then in particular, we are going to look at a slightly different setting as our framework under which we study generation, and then that is the neural dialogue modeling. So the interesting thing that we realized in about 2015, when we were working on machine translation, and in particular, neural machine translation, was, I'm sorry, so Andrea, you said we can even, oh, we can start, okay. So what we realized back then is that once we move into this kind of neural machine translation, or the neural net-based machine translation, now the source language does not even have to be a language. we could very well put an image or video clip or whatnot as input, because what neural net does is to turn the input, whatever that is, into a continuous vectors and then work in that continuous vector space. What that means is that it really doesn't matter from the point of view of the decoder in particular, whether the vectors coming out of the encoders are vectors that corresponds to language. The vectors coming out of the encoder could very well have been vectors coming out of convolutional network or the residual networks that work on images or video. And also, even if it's language, it didn't have to be a source language. That is, the machine translation system that we built yesterday does not have to work for translation. It can work to map from one sequence to another sequence, and then those two types of the sequence do not have to be two different languages. And then what that implies is that we can use the very same framework, for instance, to model conversation. If you think about what conversation is, it's simply a alternation between two speakers, and then two speakers are going to make one utterance at a time. What it means is that given all the utterances so far, given what we have been talking so far, if our system could predict what I am going to respond next, or what you are going to respond next, that suddenly becomes a dialogue model. And then that just looks just like machine translation. So neural conversation or dialogue model is the one that we're going to use today throughout the day in order to see what we can do with this kind of conditional language model. So there's on the screen, you do see, unfortunately, we can't really, yeah, so the question is that can we do live caption with the same infrastructure? Yes, we could very well do the live captioning, that's true, except that the Zoom doesn't really support it automatically. But when you go into the YouTube started to roll out auto captioning, at least for English, for some of the videos, and then it does try to use a similar technology. At the moment, they only use speech to text transcription, but eventually what they want to do is they want to use both the audio and video. So that's going to be the multimodal transcription, and then that's going to be very much like a sequence to sequence learning, where the input is not just audio, no or video, but it's both. So that's all possible, yes. So what do I mean by a neural conversation model? So it's actually conversation model, not the conversational model. That's my typo there. So think about this very simple scenario. We're going to think about only two speakers. So there are only two speakers, and then each speaker has their own profile. So we have the partner and then so self, and then each of us has a profile. So in my case, in this example, so let's say we have 4 characteristics or the properties. I'm now looking for a new job. My favorite movie is Friday. I am a doctor. My daughter is a child prodigy. So the second example is a case of having some noisy profile, right? So not everything is perfect. And then that's one of the most important points about machine learning. Data is always noisy. And then in this particular case, we have 2 speakers with the 2 distinct profiles. Of course, we don't really get to see who our partner is. So we need to learn what our, who our partner is by this conversation. And then the conversation has been going so far. So the partner said, hello, I'm sitting here with my dog. How are you? I am well, friend, looking for new employment at the moment. What would you be your dream job? So this is the conversation so far, right? And then this is going to be our input or source to our system together with the profiles. And then our job now is to try to decide what we are going to say. So up to this point is going to be the output or target. So we need to now build a system or a neural conversation model that looks at how the conversation has been going so far, and then trying to predict what the response should be. And in our case, in this case today, and then later in the first lab session, we are going to use a very, very simple neural conversation model where the input is going to be simply a flat sequence of personality descriptions. So this is the profile from the previous slide and previous utterances. So if you remember, there was a profile. So we're going to simply concatenate all the sentences in the profile. So I'm now looking for a new job, and then that's the end of the first profile, let's say description. The second one is my favorite movie is Friday. I am a doctor. My daughter is a child prodigy. And then the first utterance starts. First utterance from the partner says that, oh, hello, I'm sitting here with my dog. How are you? And then I'm going to reply. I replied already, right? I am well, friend, looking for a new employment at the moment. And then the partner replied, what would be your dream job? And then this is going to be the input. So we just simply flatten out the entire thing. So that is the what I know about myself and all the utterances that have been spoken so far by me as well as my partner. And then once that's done, we're going to simply flatten them out, so concatenate everything, and then give this as the input to our neural conversation model. And then what is going to be our target? So we need a target. Target is the ground truth, right? So in the machine translation system during training, we had the ground truth translation for every source sentence. Just like that, in simple neural conversation model, we have a ground truth target from our data set. Now, unlike in machine translation, there are so many possible ways in which the response could be generated. In other words, it's much more open-ended compared to machine translation, where the goal was to translate the source sentence as accurately as possible. And then there aren't many possible ways in which you can translate a source sentence without losing the original meaning. On the other hand, in neural conversation model, a lot can change. So given the same conversation so far, or the partial conversation, there are many ways in which the conversation can continue, even with the same person. However, what we are going to simply say is that, okay, here's a conversation or the set of conversations that have been carried out by multiple speakers, and we simply take that as a training example. And in these training examples, we have a target for every conversational prefix. And then that is again going to be a flat sequence of human annotators response. So in this specific case, I just made it up. We're going to say our target is, my dream job is to teach at a medical school, for instance. So target corresponds here, right? So far, so good. It's not really that different from machine translation. And then that's the beauty of these machine learning or the AI algorithms, is that we come up with a generic algorithms with a particular application in our mind initially, but because the algorithms themselves tend to be generally applicable, we can easily use them for another application that shares similar properties with the original problem that we designed our algorithms for. And then here, this is a very typical example where we designed an algorithm for machine translation, and now we can use the same algorithm for neural conversation model, or the or conversation modeling, which shares a similar characteristics. Now there's a question from Solomon. Can we do it on an unsupervised way, replacing the human annotation by the sentence from the text? In a sense, who wrote the text? Humans always write text. So it is both unsupervised and supervised, in a sense that the conversations are going to be collected by very natural, in a natural way. That is, we're going to let two human speakers talk to each other. So yes, the answer is yes and no. But later on, if I remember correctly, in the first lab session, we're going to see that building this kind of conversation model is difficult. Therefore, we tend to pre-train these models on a web form data sets. for instance, from the Reddit. But you're going to hear more about it from Shreyas later. So let's just review quickly what we mean by the neural machine translation system, and then there is conditional language model, right? And what do we mean by the conditional language model? We learned about it yesterday all together. So we are going to have some input. There was a source sentence. And then you know, in this case, we're going to have a flattened sequence of all the previous utterances and the descriptions of the speakers. And then given that, we do the language modeling. So given the input, we are going to do the language modeling, that is trying to capture the distribution over the response, Y in this case, and we do so using the autoregressive paradigm. That is, we rewrite the probability of the sequence Y given X, the input, or the previous utterances, as the product of predicting the next token given all the previous tokens in the response and the input, that is all the previous utterances. And then if we put it in a graphical illustration, what we see is that we have the input X here, and then we have the encoder G, and then we have a decoder F, and then this decoder is going to be always conditioned on the output from the encoder. And then this F, the decoder, is going to generate one word at a time. And then that generated word goes back in. And then we do that over and over and over, while carrying over the hidden states from one time step to another. And this is what we mean by neural conversation model as neural machine translation, or more specifically, conditional language model. So how do we learn that we're going to learn this kind of system? Is to use maximum log likelihood learning. And then what does it mean? That is, we're going to use the negative log probability of the correct or the ground truth response given all the previous utterances as our loss function. How do they actually correspond to each other is because when you maximize something, that's always equivalent to trying to minimize the negation or the negation of whatever you're maximizing. So what it means is that the max of log P of the correct response given the previous utterances is equivalent to mean G and F, which are the encoder and decoder of the negative log probability of the correct answer given the previous utterances. And then that can be written down as the sum of the log probability of the correct next token given all the previous tokens, all the correct ones, and the previous utterances. And then we sum them over all the time steps, going from first time step all the way to the end of the time step. So that is the length of the entire sequence. And then we learned about this yesterday over and over, and day before over and over, when we talked about how we train this kind of language model and the machine translation system. And in the lab sessions, you learned how to estimate all these quantities, either as a count-based n-gram or as a training a neural network. So at the end of the day, what we're trying to do is that given all the previous utterances and the descriptions or the personality descriptions of the speakers and what has been responded so far. So that's going to be the partial sequence of the response, trying to predict the next token. Yes. So what we are talking about is all just open-ended, open domain. It's a chit-chat setup, and then there is no task associated with any of these conversations. And then there is a question from Danielle about whether we can go through the y max log is equals to the mean minus log p. If you think about it, let's say I have some function. So this is going to be my theta. So this is going to be the parameters. And then here's some function. Let's say this is a loss function that I want to change, right? loss of theta. Let's say this function looks like this. Now, trying to do the max, so if I want to find the max, let's say this is a max, is identical to, I'm going to change the color here, to computing, I'm going to just flip it, so this is going to be minus L theta, trying to find the mean. So you look for max is identical to finding the mean in the negative, right? Makes sense? And then another question from Joseph is, for conversation, what is X? Is it all the previous conversations, many sequences? Yes, the answer is yes. Let's go back here. We talked about it. So this input is X. Let me change the color back. So here the input X is the input, and then as we said, it's a flat sequence of personality descriptions and previous utterances. Of course, it doesn't have to be a flat sequence. We can think about making it to more like a graphs or the hierarchical structure. However, for this lecture and then for the lab session, we're going to stick to this flat sequence, which turned out to be almost as good as having a more complicated way to represent it. All right, sounds good. Now, and then we know how to train this pretty well, right? So we learned about it for 2 days, so we can train it however we want. I'm sorry. What is this thing? There is a weird thing here. Let me just. Okay, there we go. Oh, there was a weird annotation. I'm sorry about it. So let me just, I have to go through the how we build the data again, because I think that a lot of people are confused about this. So important thing is to notice that the input to this neural conversation model is what has been spoken so far, everything, including what I know about myself. So that's going to be my profile. So this is what I know about myself. And then what has been spoken both by my partner. So these are both by my partner as well as myself. So given these setups, now what should be the output? This is the neural conversation model. This is very important to remember, is that here we are simply turning this problem of conversational modeling into the machine translation by mapping what has been said so far, plus what we know about speakers, including myself, as the source sentence, and then now target the translation is going to be what I'm supposed to say next, or what my partner should say next. And we have learned how to do so very, very extensively over the past 2 days. And then we can use for instance, the gated recurrent units, long short-term memory units, all the self-attention that is transformers here, to build this kind of neural conversation model. However, it turned out that the one thing that we haven't really talked about that much, although Pooh as well as Sean touched upon them, is how we can generate from this system. Once we train this model, in order for us to use it, we have to be able to find the response given the input that's going to maximize the log probability of this. So what our system computes is the distribution over all possible responses given what has been said so far. So given what has been said so far, our system computes the distribution over all possible responses, where the all possible responses is indicated by this set. And then what we now need to know is, what is the particular response that receives the highest probability according to our model? And then that is the problem of inference or generation. Unfortunately, the number of all possible responses is extremely large. In fact, the size of this set of all possible responses grows exponentially with respect to the length of the response. let's just imagine where we are going to say that the maximum length of the response is going to be 500 words long. That's a bit excessive, but who knows? Sometimes we need to ensure that the response can be as long as it could. And then for each location, or the size of our vocabulary is going to be 1 million. Or more realistically, let's say 50,000. Then the number of all possible responses is going to be 50,000 to the power of 500. And then that number is gigantic. There's no way we can actually exhaustively try every single possible response and then pick the one that has the highest probability according to our model. When we put a severe restrictions on what our model computes, such as the strong Markovian properties, as in n-gram language models, or the linear constraints, as in the state space model, or the Kalman filters, which I believe you may have learned already during your AMI courses, then we may be able to solve this more cleverly by using some kind of dynamic programming procedure or the gradient descent algorithm. However, in our case, we do not really have such constraints. And then what we know is that putting any of those constraints tend to make our sentences less well-formed. So we don't put any of those constraints. And then what it means is that we don't really have a way to solve this problem of generation or trying to solve this argmax problem exactly. And we have to rely on approximate sequential local search, such as a greedy search and beam search and few others. And then we're going to go through each one of them one at a time here. First, what is the greedy search? Because we cannot solve this problem perfectly, we're going to choose the best symbol at each time step separately. So what does that mean? Is that instead of solving this is too difficult, we're going to simply say that at each time step t, our answer is going to be the argmax of yt over given this conditional distribution. And this conditional distribution is defined over only the vocabulary, right? And then the size of the vocabulary is only 50,000. So we can exhaustively test all possible tokens. And then that's easy. We simply compute the softmax from our decoder, right? And then we're going to look at the log probabilities assigned to all possible next tokens, and then choose the one that has the highest score. And then that's very straightforward to compute. And then if you think about the computational complexity overall, then it becomes, so we're going to use the big O notation, O of size of the vocabulary times T, right? T is going to be a max length of the response, right? And size of the V, this is the vocabulary. This is very natural because we are going to simply look at the entire vocabulary once at each time step until either the end of sequence token is selected or the maximum number of the length is met. Now, this is very different from the exact problem that we want to solve, which requires, in the case of the exhaustive search, O of vocabulary size to the power of t. So this was exponential. It's too expensive. We cannot really solve this problem exactly. So that we will go for the greedy search. This is one possibility where we're going to simply choose the argmax at each time step, regardless of how well the choice is going to impact the future. This is heavily suboptimal in a sense that it doesn't really take into account the future consequence. What do I mean by that? So how do I know whether choosing this YT hat is going to impact the log probability I'm going to get in the future? We don't really know. There is a reason why it's really expensive to, or the computationally infeasible to solve this problem exactly. Furthermore, we commit to the only this, we commit to the decision at every time step, and then there is no way we can revert the decision. We don't have an ability to go back in time and then revert the decision. But somehow this is like one of the most widely used in neural dialogue generation, unlike in machine translation where we have been using beam search from the very beginning. So greedy search is too suboptimal, so we want to be slightly less suboptimal than greedy search, and then that's where we go into the beam search. As the name suggests, what we do is instead of committing to one decision at a time, we're going to carry over multiple possible decisions or multiple possible beams in this case. So we're going to look at this graph, let's say illustration or the animation here. So we start by looking at the very first step. Let me actually erase that and then redraw it. So we start from the T1. We're going to look at the entire vocabulary to figure out what could be the good first word in this response. And then in particular, consider that we have two hypotheses in our beam or in our set. So we selected two of these, and then given these two, for each case, we're going to look at the possible candidate set. So for each candidate, we can expand it by looking at the entire vocabulary again. And then that's why we have the two blobs here. And then for each blob, we have the vocabulary size many candidates. And then among them, we're going to look at the score coming from the prefix and then choose two again. So we selected these two. And then given these two, again, we are going to expand them. Now we get another, let's say, two of this. However, and then we're going to select, again, two of them, right? Based on the prefix. Now what it means is that in this case, this particular one, the red one, was dropped from the beam. And then that can happen because we have to somehow limit our computational budget. So what it means is that we cannot just carry over everything. We have to sometimes drop some of the hypotheses that we have been carrying over, and sometimes we expand it. But generally, it's going to narrow down the search space significantly over time. And then we do that for multiple steps until all these beams terminate. And then once everything terminates, then we're going to look at the score so far in order to choose the best one among all those hypothetical or the hypothetical prefixes or the hypotheses. And then this beam search is really nice in a sense that it does take into account the future consequence up to a certain level. So we did not choose this red one because we knew that if we consider the future, this blue one was better. And then furthermore, we can now control the complexity by changing the width of the beam. So the computational complexity in this case is going to be O of course, it's always going to be linear with respect to the time. And then it's going to be linear with respect to the vocabulary size as well, up to a certain level. But then we do have K, another linear factor. This is the size of the beam. Now for the beam search is really important because we use this everywhere, from machine translation system, neural conversation system, image caption generation system, even speech recognition system relies heavily on beam search. And the beam search is not only for these neural autoregressive models, but other paradigms as well, such as the CTC, connectionist temporal, what did the CTC stand for? Connectionist temporal computation or something like that, it doesn't really matter. Or the hidden Markov model as well, you really need the beam search. So we do not use the backtracking in this case because it's very unclear what is the right way to do the backtracking. Backtracking helps a lot in beam search if we know how much further back in time we should backtrack and then restart, except that in our case, we don't really have a nice notion or the nice concept or the quantity that we can use to backtrack and then restart. Now, that one is going to be connected to the uncertainty in neural network. However, in this kind of autoregressive model, we're not entirely sure what is the right way to characterize the uncertainty in this kind of neural network. And then there is, of course, no guarantee that this beam search is going to find the best translation. It is still approximate search because, again, exact search is intractable because the size of the hypothesis set grows exponentially. On the other hand, beam search, the size of the hypothesis or the translations that beam search considers is only linear with respect to the size of the beam. What it means is that there is a discrepancy here, right? And then this discrepancy makes it nearly impossible for beam search to find the actual best candidate the model can provide. Of course, for some examples, maybe, but other examples, maybe not. And it's very unlikely that it's going to work to find the best translation for most, or if not all of the examples. So what happens in beam searching? Let's look at it in detail. So at every time step, we have the hypothesis that has been created so far. That is, so this is the hypothesis set at time t-1. So this is the hypothesis set. So H indicates the hypothesis set. And in this hypothesis set are prefixes. That is, this is the word choice at first time step, word choice at second time step, word choice at t-1 step. And then this is a one particular hypothesis. And then this hypothesis that consists of the multiple of such hypotheses. And then given each hypothesis, we can expand it, right? So here, the first t-1 tokens with the index k corresponds to the kth hypothesis in this hypothesis set at time step t-1, that is ht-1. And then we can expand it by attaching it with one of the tokens from the vocabulary. So we're going to look at how it can be expanded. And then we end up with the k by k candidate hypothesis, right? So we had the size k hypothesis set from time t-1. For each hypothesis, we expand it by one token from the vocabulary. But then we don't really care about the entire vocabulary. We're going to only look at the top k of them. So that's why we end up with a k by k. Once we have them, then we're going, among all these k by k hypotheses, or you can also think about it more naively as k by the size of the vocabulary hypothesis, we're going to select the top k next hypothesis in order to construct the HT, that is the new hypothesis set at time step t. And here, we're going to use both the score or the log probability from our model, as well as some regularization term. You may have learned about the regularization already in the introduction to machine learning courses or the deep learning courses earlier on. Even for generation, we need some kind of regularization often. We're not going to go into much of the details, but if you want, leave the questions in the campus wire when the service is back online, and then I'll be able to put some papers or the papers that you can read further in order to learn about what kind of regularization could be used or they have been tried by people for beam search. And then once we have this new hypothesis set, we just repeat the whole procedure again. So we're going to go back and forth between constructing the new hypothesis set, expand it, construct the next hypothesis set, go back, expand it, construct the new hypothesis set until all the hypotheses terminate with the end of sequence eventually. And then you're going to see how this is implemented in the PyTorch together with the Shreyas in the first step session today later. Let's just look at it from the animation, which is so much easier, right? Now, I have the k-many, so I have k-many hypotheses at time step t-1. And then what I do is I expand it by considering all the tokens in my vocabulary V. And then given that, I can now select top K from each of the expanded versions. And when I look at the top K, the score that I consider is the score of the entire prefix. That is a sum of the log probabilities so far, not only the log probability of the last one. That's very, very important to know. And then once I do that, I'm going to do the top K selection from the concatenation of the entire all the expanded candidates. And then that's going to form our next hypothesis at time step T. And then these are going to go back, and then we try it over and over until every hypothesis ends with the end of sequence. More globally viewing, if you remember from the earlier graphical view, so you can think of these two tokens as these two in the hypothesis from the previous time step. We're going to expand them, so these are going to correspond to the expansions. And then within them, we're going to select two of them, that is the top K selection. So these two corresponds to now two selected ones, right? So this is what happens. Now, let's go back in time quickly, and then I think there is a one confusion here. So here, what is the size of this HT? So HT is the all possible prefixes up to T, and then, oh, actually, you're correct. Sorry about that. Thanks, Joseph, for pointing this out. This should be this instead. That is, what are the number of all possible sequences up to time step T is the size of the vocabulary to the power of T. That's correct. So this is wrong. All right. Thanks for pointing out, Joseph. Oops. So let's go back. Okay. So in this global view, this is what happens. So you see the correspondence between how the beam search is exploring the space of the all possible sequences. So this is a space, oops, space of all possible sequences, right? And then how beam search is exploring this space, and then on the left side of this slide corresponds to how it does so at each time step locally, right? So of course, beam search works reasonably well. However, beam search is not perfect in the sense that they often ends up with a very, very similar hypothesis eventually, as you could see from this kind of example, because they are going to always share some kind of prefixes. And then the reason being that we don't really have a nice way to identify what are the similar sequences and what are the dissimilar sequences in this discrete space. But that's kind of beyond the scope of this course. So then you can think about actually coming up with the different types of the beam search algorithm, or the expansion or the advanced version of the beam search algorithm. One particular instance is called Iterative Beam Search algorithm, which was inspired by the diverse beam search algorithm by the Lee and Jurowski, as well as Dhruv Batra et al. From 2012. So the idea is that you're going to run the beam search once, and then you're going to run the beam search once more. But when you run the second beam search, you're going to ensure that the second beam search avoids any search subspace explored by the earlier iterations of the beam search. So when we run this second beam search, so I'm going to delete some of the things here. So we ran the first beam search here, that is colored by the yellow. But then when we run the second beam search, which is marked by the blue color, we're going to intentionally downweight or set the log probabilities to -infinity for any prefixes that were explored already by the previous iteration of the beam search, so that you can actually use you can force the second iteration of beam search to explore different parts of the space. And then the nice thing is that this leads to a higher diversity in the sequences or the prefixes that are being explored or considered. And also there is no additional hyperparameters. You just run the beam search over and over until your computational budget is satisfied. And of course, this is a variance of the beam search, but we can also go for another type of the inference algorithms that is based on the sampling. Hold on. Yes. Sampling. That is, instead of trying to find the best sequence, a single best sequence eventually, that is a deterministic algorithm, we can simply say that, okay, finding a single best sequence deterministically is unrealistic. So instead, what we can do is we can simply sample number of the sequences and then look at all those sequences and then choose the one ourselves. And then, of course, the best way to go is to simply sample from it over and over. But it turned out that the sampling from the entire sequence is not that great because the space is too large for our model to put a high probability only on a very good stuff, only on a very good responses. It's going to always, because of its imperfection, our models are going to put some non-zero probabilities or the high enough probabilities to nonsensical responses or translations almost always. So what we want is for us only to consider those sequences that are likely to be assigned high enough probabilities and ignore any responses or translations that are going to receive not high enough probabilities. And then we can do that by considering only top K tokens at each time step. So we're going to sample from the distribution. So we're going to go through each and every time step our softmax. And then instead of sampling from the entire vocabulary, we're going to only consider small number of vocabularies whose rank when sorted according to the softmax probabilities are higher than K. So we're going to only look at the top K words according to the probabilities assigned to those tokens by our model at each time step. And then we're going to ignore all the other steps. Now, the interesting thing is that this kind of, let's say, confusing what is the induced distribution here, because does that actually correspond to what this model actually learns? I don't know, maybe, maybe not. It's a bit confusing, it's difficult to tell. However, it turned out that this kind of top K sampling works reasonably well, and there have been a number of the variants that have been proposed, which we already have seen earlier. And then you can think of this as a variant of introducing a temperature parameter to a softmax and then setting the temperature to be very, very low value. We actually don't use this kind of sampling algorithm for machine translation because of the stochastic behavior. It's going to be really, really weird if you think that what you use, when you use, for instance, Google Translate, and then trying to translate one source sentence, and every time you run it through Google Translate, the answer, the translations change. That's not really good, right? So we want to build a system that is more or less predictable or has a predictable behavior. So what you want is to have a deterministic behavior. That's why this kind of top K sampling is not really used in a production systems as much. And then what do I mean by temperature? You should go back to the campus wire. There are some questions related to temperatures, and then there are answers to that as well. And I believe that in the first, on the first day, we actually did talk a bit about the temperature. I believe Strauss will be able to mention temperature very briefly in the first lab session, but it's not really important. We don't really use them that much. So one thing that is slightly different from machine translation, when we think about the neural conversation model, is that the evaluation is extremely difficult. In the case of machine translation, we talked about the blue score, right? Blue score is not perfect for sure because it's an automated metric and it requires you to have a reference translation. But we have seen, and the people have shown that the blue score, when the system, machine translation system is reasonably good, correlates quite well with the human judgment of how good a translation is. However, in the case of neural conversation system, especially in chit chat, it's impossible to tell whether a given response is good simply by comparing a generated response against the reference response, because there are so many possible good responses given a partial conversation. What it means is that the single turn evaluation, that is, given the correct conversation so far, what should be the next response? That is, the single turn evaluation is simply not enough. We cannot rely on that. And then there are many theoretical reasons why it's not enough, but that's kind of out of scope of our course. But it's quite easily understandable that because of the diversity in good responses, the single turn evaluation is not enough. Therefore, what we need to do is the multi-turn evaluation. That is, we build this kind of neural conversation model and then ask this system to talk with a person in reality, and then ask the person after the conversation how good the conversation was. If the human speaker tells us that the conversation was good, then our system is good. If our human speaker told us that the conversation was not good, then our system is not good. So we have to have this multi-turn evaluation, which can be quite expensive financially, because you need to recruit these human annotators. But also, it's very difficult technically due to the noise. Not every person is good at gauging whether another person or the partner in conversation was good or not. So in order to do this kind of multi-turn evaluation with the human evaluators, what we need is not only simply collecting the scores and then reporting the average scores or its variance, but we need to do the calibration. Why do we need the calibration? Because people have a different standards and then different kind of, let's say, baseline to tell whether a system is good or not. So here's one particular example. So one of my PhD students and I ran these experiments, and then the y-axis corresponds to each of the human evaluators. So 0 corresponds to one human evaluator, 1 corresponds to another human evaluator, 2 corresponds to yet another human evaluator, and then we tested for 11 human evaluators. And then this is from one system. So we built one system. We tested with the 11 human evaluators to make multiple conversations with the different topics and different personality descriptions given to both the humans as well as our machines. And then we asked our human evaluators to score all those conversations. And then it turned out that even though it's the same system, some evaluators, such as the annotator number 10, was extremely harsh. That evaluator said that this system really sucks, generally. On the other hand, evaluators 4 and 5 said that this system is amazing. This system just worked amazingly for them. And then some of the evaluators, such as the evaluator 0, says that, okay, it's on average. What it means, and then what happens is that it's not because the system is all random. It's more because people have different levels of expectations. Everyone has their own level of expectation, and it's more like the variance or the variability in human judgment system. So what you need to do is to calibrate the evaluation as well. And how do we calibrate it? There are many different ways to do the calibration, and then it is quite straightforward these days to use a Bayesian calibration or so-called model-based calibration. And then in model-based calibration, you're going to build your own model of how the human annotators works. And in our case, we say that the human annotators have some kind of bias to be either harsh or generous. And then there is the unknown hidden model score that is mu with some noise in it because system has its own variation. And then they are combined additively in order to become the actual observed score. What it means is that whatever the score we observe is the combination of how well the system actually works, plus how harsh or generous the annotator is. And then once we build this kind of model, we can use Bayesian inference in order to try to figure out what the actual distribution of our model score is, given the observations of the scores, or the scores given by the human annotators. And this is really important to know that whenever you do the human evaluation of these language generation systems or any kind of complicated generation systems, you have to calibrate, calibrate for the variability in the human annotators or the human evaluators. Otherwise, you may be looking at some scores that are not really well calibrated and misleading as well. Now, one thing to tell you, if you can get as many annotations as possible, that is almost infinitely many of them, average scores are still going to be meaningful. But often, because of the cost associated with collecting all these human evaluations, you cannot get infinitely many of them. And then you have to run this kind of model-based, or could be model-free if you want to be the frequentist, calibration. Otherwise, whatever you report or whatever you use to decide which system is good enough to be deployed in practice is not going to be a good decision. So, does that actually make sense? Let's look here. When we look at the calibrated score, it turned out that these are the calibrated scores. Using a better search algorithm does give you a better score. What it means is that interestingly so, these language generation systems must be used with good generation algorithm as well. However good your model neural net is, however well you train a model, with however good the data that you have collected, if you do not use a good inference or the generation algorithm, your system is not going to work as well as it could. In other words, you should always consider what kind of generation or inference algorithm you are going to use. And then you need to consider both the computational budget as well as the quality of the generation algorithm. And Shreyas is going to show you in practice what it actually means. And just one thing you notice is that if you don't do this kind of calibration, the standard deviation is too large for the scores that you collect, the raw scores, to be meaningful. So you always need to run the calibration to get the meaningful scores out of it. So that actually does conclude the first lecture of today. Due to the schedule, we will have to be back in about 15 minutes for the second lecture. And then after that, you're going to have some break until we start again with the lab sessions. So be back by 8:15 in New York time, and from the let's say what time should that be in Kigali? In Kigali time, hold on, let me just look it up. I think there anyway. So be back in 15 minutes. I'm going to send an email. Let's see if Campus Wire is back online. Campus Wire is still not back online, so I'm going to send an email again, but please be back in 15 minutes. Then I'll talk to you later then. Jama.